Okay, iced tea on hand. Let's try something different today. How about some image recognition? My beloved little Vector is sleeping. Oh no, it's probably gonna wake up. Hey Vector! Hey Vector! Go to sleep. Open Twitch chat.
Open Twitch chat.
So Vector has a camera, obviously, which makes images like this one. The original resolution should be higher. Actually, it should be 1280 times 720. For some reason we get a scaled down version. But it's definitely enough resolution to work with. What can we do with this image? Let's say I want to find the home station, because Vector is not 100% perfect in finding its home station, I think. If it's hidden from view, okay, then Vector's brain is overloaded anyway. But if it's in view, even then sometimes it doesn't see it, I think. I mean, it's pretty good, usually it works. But I want to try my own hand in this. I have an unusual approach, I think. It's called integral images. This is one single transformation of an image where basically there are sums being made. And these sums allow you to scale down any part of the image to any size instantly. Instantly means every pixel has a constant computation time. And the extreme case of this is reducing whole areas of an image to 1 pixel. That also takes one step. I did the measurement once, 2 nanoseconds roughly is how long one step takes. So you can do almost 1 billion of these every second. 1 billion pixels. So it's really fast, and we can. The challenge is to determine where to look in the image. You get an image like this one, and the home station could be anywhere. It could be in the corner, it could be in the middle, it could be big, could be small, could be very small. Very small is probably the hardest, but let's say it has a reasonable size. And we just scale to some size. We can scale the whole image using this integral image technique, so it's very fast. This would be 64 pixels width and some corresponding height. And this is 4 times the resolution. 64, 128. And this is already good, right? Here you can see the station and the symbol on it. That should be great to work with. So we could, for example, scan this whole image. That is again going to be slow. If you convolve a snapshot of this here over the whole image, that's going to be slow. You're wasting the advantage you get from the integral images a little bit. Maybe it's still fast enough. But an even smarter approach is to take a downsampled version. Let's make one that's even more downsampled. Here. And here you can skip areas, obviously. This completely white area can obviously be skipped. We need something where there's at least some busy pattern. So yeah, image recognition is it's a really real challenge. There are so many possible approaches to do it. My text processing frameworks are reaching a very good point now. With the image processing, I'm still experimenting with lots of things. But let's say, well, we really have multiple problems at once. We have scale, this image can be bigger or smaller, and we have distortion. You can look at it from an angle. We have different lighting. And what else do we have? It's a part of it might be cut off. I mean, this case we are going to ignore for now, I think. Yeah, we have size, position, distortion, and lighting. That's quite a lot. If you want a fast image recognition, you will have to do multiple stages. As I said, first find the rough position. You kind of have to assume that something bright is around it, otherwise you're not going to see it at all. I don't know. I mean, this image you could have candidates, because we are looking for a roughly square shape. So there are mostly like two candidates, this one here and this one here. Yeah, that should be an approach. I always thought that there might be a cheapo, a cheap way to go about it. You would simply scale this to a certain size, like here, and just grab portions of it here. Grab this rectangle, because you know, this is the training stage where you know what you're looking for. So you grab this part here, save this. You could do the same with the cube. At this point they look similar. This looks a little different, but theoretically each of these could be either the cube or the home station. But it doesn't matter. At this stage here we are looking to reduce our search space to find the area in the image that interests us. We can discard all of this and this whole part here. We really should get these two candidates. If the resolution is not too high, we can just do a full scan over the image. We take our little sample images, which are just blobs. We take these images and move them over the whole image, and we take the best candidates. And in these areas we pursue further. And then we go to a more detailed view. Next step, we might go here. The 64 pixels version. And we do the same thing. We also take images from the database that we made at some scale. The image we're looking for could have been made at a different scale with different downsampling. It just has to have the right pixel count. And then we're one step further. We could even start to say this is probably a cube and this is probably a home station, which we could have done here already also. I mean, this blurry image, it always gets easier when you make certain assumptions. When you assume in the scene there should be a home station and a cube, and then that goes a long way. Under this assumption, pretty much you can guarantee that these two are the ones. Yeah, so what about different sizes? What if we have an image where vector is closer? Let's see. Hello. 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 Yep, it takes quite a few pictures per second. I'm guessing at least 3 FPS or roundabout. Okay. Yeah, what about this picture here? Vector. Let's resample. Yeah, let's call it example 2. CD pictures, CD vectorcam, copy 4759, example 2 JPEG. Oh, we just had this, and what do I want to do? I want to sample to these 3 levels. It still holds. This pixelated version here should be fairly similar to what we had in the other picture here. Yeah, because this is closer, but we downsampled more. So get the same kind of pixel image. And when we scan the image for these prototype images, we just subtract. I mean, there are different ways. Yeah, the naive way is just to go pixel by pixel and say, and add the differences that we find. That's actually a good way when the lighting is fairly constant. If the lighting varies a little bit, it's okay. If it varies a lot, then it might begin to be a problem. But it's often still okay, because even if the whole lighting changes, this area is still going to be the most similar to our prototype image. Even if the prototype image was darker or something, because this is just way different and this here is way different. But it might start to get errors. Another way is something called HAR features, I think. HAR features.
Heart's fixtures.
HAR features. Oh,
Harsh features.
wait. Oh, yeah, I know. Wait. HAR-like features. No.
Harlot features.
HAR-like features. Yeah. Is there any image? No. The basic idea there is that you. Oh, come on, where are we? That you subtract the dark from the bright pixels. So any difference in brightness will be calculated out because you basically have a bright and a dark portion which are of the same size, and you subtract one from the other. I explained this really badly. But it's one trick to get around the lighting issue. I mean, I have done implementation of this stuff before. Face Finder. At this point, the challenge usually is to find my code that I used to make, or have made, because my repository has gotten so big. Face Finder training. Live webcam face finder. This will not work because the webcam is in another program. Eyebrow finder, yeah, that's also a good one. Let's dive into it. Face. Marked faces album. Yeah, there's a few faces. This is the same principle. We take some pictures and mark something of interest. No face, some face. Beard, no beard. And then we can train something on that. Face finder by pictures. Is that the one that works? Yeah, this does the image search. It takes a color image though. The color images seem excessive for what we're doing. Let's add some comments. Works on RGB image. Searches for patterns by raw search. Or scan. Yeah, that will not scale for many patterns or whatever. Yeah, we will have multiple patterns. That's another challenge to manage a database of prototype images. The trick would be to make many snapshots of this thing, and then when you train the recognizer, you trim down the set of prototype images. You just take out, you try taking out images out of the set, and you see if the performance of the recognition degrades. And then you take out the image that does the least degradation to the recognizer performance. And you do this as long as the performance is still adequate. So you might go from 2000 sample images down to whatever you want. Maybe it's 20 or less. Maybe 20 perspectives of this particular object are enough to do a good recognition. And there will be multiple stages anyway, so you can, if you have more time for the recognition, you can look more closely. There's always a first short phase where you do a rough scan over the image, and you don't always have time. If vector is moving around, you want quick results. 100 milliseconds at most, and you want a result. Where do I have to move? But if it's standing still and it has nothing to do, you can do more. Or if it wants to fine-tune its position. Let's keep looking for things that already exist. Face Finder. Face Finder X1, that's the one we just looked at, isn't it? No. No, it's a different one. Okay. That's a trick thing, more or less. Just looks for a dark blob. If you have a bright background and your face is the only thing in the image. This one does something sneaky, something simple. Train Face Finder, yeah, this is a simple one still. Starbucks. It's my training images from when I was at Starbucks. Eyebrow Finder, Live Webcam. I do not see any other classes here. Okay, where's my goal window? Goal today is different. Goal, find vectors charging station in images. Taken by its head camera. Yeah, virtual scaled down image. Yeah, this takes one of these integral images, these clever image representations, and gives us a scaled down part of it as a virtual image that we can query pixels in. That's also pretty good. And first we need to label some training data. I can in fact mark something here. That's a function that this image surface has. So let's say I do this. Yeah, subgoal mark some images for training. Oh, let's do something funny. All image surfaces. Oh, swing. I have this very interactive system where I can just make Java code that inspects everything that is running in all my Java stuff. So for example, I can get all the visual components, all the text areas, all the windows, everything, all the buttons with one command. So there's 1027 things on Java space short named filter short name filter by short name image surface. These are all the image surfaces. There are 11 of them right now. One of them is the one I want, where I just marked this. Okay, let's do this first because that's cool. All image surfaces. They are JComponents. All image surfaces. Ta-da. Nope. Yep. Okay. Let's get the selection of all of these. Yeah. In fact, only one of them has a selection. So now we have the coordinates we wanted. And we can get the frame title, for example, and display this. Oh, it's a rectangle. There's that. Let's get the image. And then we can, for example, clip. Clip buffered image. Yeah. Come on, Java. It's not that hard. Yeah, up here, very small. We have the cropped image of this charging station. Save it. Pictures. Vector cam. Charging station. Pics. Pick one. Yep, there it is. Now, if we scan just for this one image in loads of test images. I mean, we could take more here. Yeah, let's see about that. Let's say we grow it by 1 pixel. What would that look like? Yeah, like this. It may or may not be a good idea to take 1 more pixel. Here, now we have... This is kind of assuming that there's white around it. The more pixels around it we take, the more we are dependent on the background, which is not very good either. Or you may just save it, why not? Save image. Pictures. Vector cam. Pick with 1 pixel border there. Okay, let's go to all the pictures in the vector cam directory. List image files. List image files. Seems to work. File. Yeah, whatever, we just go through them. have number of images. Yes. And we transform them to an integral image. Let's see maybe how long this takes, just this process of loading them all, converting. Takes a bit. Let's take it again, try it again. Okay, pretty much the same time. Yeah, but you do this transformation once. Let's see if it fits in memory. Integral images. New. How about oh, it does. It does accept a file. That's good. Ah, I programmed that well. Directly paste the file in there. Image files. So we do this once and not every time. That's a smart idea. Just have to store it somewhere. Yeah, I wanted to see if they'd fit in memory. If there's any problem. Right now, 899 megabytes used. My P call. What's happening? Aha. Uh, 830 megabytes, 972. Still loading. Yeah, it went up a little bit. Nothing to worry about. Okay, so we can load all these images. I mean, we don't have to do that. We can do it. Yeah, one at a time. Okay, where's our prototype image? Charging station. Picks. Pick one. There's the prototype. Why doesn't this convert back to an image? I mean, that would be pretty cool, actually. I think. Get buffered image. Yep. It's a bit of a waste, but we'll improve. Yeah, we'll make it faster eventually. Okay, where was I? Here. Just some easier conversion. Get buffered image. Scale down. Scale down. Unoptimized. Why did this ever work? How did this ever work? Oh, I changed it. I don't know. Doesn't matter. Show image. Mix buffered image. Maybe this one is the same deal. Yes, it is. That's good. Stormy outside. Yeah, it's showing us the image. That's all I wanted to do. Yes, and it also has the charger inside in a different perspective. That's kind of interesting. Let's look for the charger picture in this image here. This is the one we're searching in. This is the image we are looking for. We might want to close some other windows here. Yep. And that. And that. So we just decide on scale. We decide how to scale down this one, which we can also do to get an even coarser representation. But I like this level of detail because you can still see the important details here. This seems to me is a good level of detail. Maybe a little finer, but it's okay. And yeah. I haven't done this before, I think. Search an integral image. Oh. There was something like a raw search function. Yeah, raw image search. Quick and exact. What was this difference? Yeah, image section similarity. This just does the pixel. Think. Does the pixel by pixel comparison and adds all the differences. Returns something between 0 and 1. 1 being identical and 0 being completely unidentical, which is rare, I think. You almost can't get that, only with complete white and complete black. Otherwise you don't get 0 similarity, I think. Think. Yeah, okay. I really want to know, why is there a quick and an exact version? What's the difference? I should have made a comment here. If identical? Oh, exact means perfect match. Only finds perfect matches. That's good to know. This one gives us a number, it gives us multiple results actually. You put in a max error value. Yeah, you put in the minimum similarity you want and it gives you all the image positions. There has to be one that gives you just one result. No? Find image all. Where's the find best match? Search best. I'm really confused why I don't find this or don't have this. Return best match, that looks like something we want. Virtual pig, whatever that is. These are things I coded a few years ago, so my head has a lot of capacity, but not infinite. And it prioritizes a lot. Return best match, here we are. It also takes a minimum similarity, and then it finds the best match above that. Cool. Big pad flare, okay, that's doable. Image search best. Min similarity. Big image is the scale down version. No, what? Scale down using image to the width we want. Okay. What did we use? I think 64 was a good value. And start at 90% similar, maybe. It started whatever, started 0. Give us any match. It's the one we search in, and the pattern is the prototype. And we just print. Interesting. And now the big question is, how good is the match? Show, yeah, first we print. Show image with selection should work. Let's show this one. R like a rectangle. Oh, come on. Show image with selection. Selection. Zip. Okay. I can work with that. So show image with selection. Let's make the complete function while we're at it. Oh, drum roll. Yeah, it is the position of the charger. Here. Even though, I remind you, we took an almost completely different picture. Well, not completely different. It's from a different perspective. And the scale is not right. But it still found the right thing. And if this first step is wrong, there are further steps down the pipeline, depending on how much time we have, which will look further and also explore alternative results. Maybe if we look for the two best things here, yeah, that should be a function too. Then could return this here maybe also as a second result. And then the next pipeline stage would also investigate here as soon as there's some time. It's like a time management thing. We have a time window of, I said, 100 milliseconds. And in this time, we try our best to find the object. This is a process that can be optimized by meta algorithms. Actually, I mean, this is pretty cool already. What if we try different scales here? If we make it a little smaller, let's check that. Also, we should pixelate. Okay, let's see. Show image pixelated. Show image pixelated zoom to width. With selection, that's what we want, right? Set selection. Compiler, don't let me down. Oh no, you let me down. Well, human error. Oh yeah, wait. Almost. Set selection doesn't exist. That's unfortunate. Okay, now it does. Did we make the compiler happy? Let's find out. Oh, that's nasty. Ah, now we cannot put null anymore because null could be this or this. Oh, holy moly, no. And dear Java, sometimes you are annoying. I don't think there is a good way to make the compiler accept null for this function anymore. I don't think there's a trick even, like a good trick. So we really have to put in something here, like cast null to a type. That's just a joke. That's just awkward. Need more iced tea after this shock. Sure, I forgot something here. Yeah. Best iced tea in the world. Lipton Sparkling. Okay, and a different. Okay, but it was the wrong direction. I scaled it down, and the picture we're looking for is this big, so it's not a very good fit, but it still found the right spot, basically. This is surprisingly robust. So if we scale it up a little. Finds it, no problem. Let's see how long the actual search took. Search will be faster when we raise this value here. Time image search. Let's just see. 83 milliseconds. Oh, this is a micro benchmark or whatever. It's not a rigorous benchmark. Java gets faster when you do things multiple times. Okay, a higher starting similarity didn't really change anything. 110 milliseconds. That's actually slow. Where is our problem? Why is it slow? It does have to move this image over the whole image. Yeah, we should even now have a step before that on a coarser scale and then look at only some areas. Or you can skip some pixels. It goes pixel by pixel, one pixel further, the whole row, and each time it checks the whole sub-image. Unless it finds out that it's already too different, then it quits halfway. And then it moves over the whole line, and then it goes to the next pixel row and applies the test image everywhere. So it's quite a lot of effort. Yeah, contradicting what I said earlier, that this is such a fast method. Yeah, image recognition is a challenge for sure. What if we just run this 10 times? And then we measure again. Let's see. Okay, now it's 5 milliseconds. See? That's how Java works. Do something a few times, it gets compiled and optimized in the background. Now we're at 5 milliseconds, so way better already. Yeah. And the one thing I really need here is just a GUI and a nice tool to train. So training has to go back and forth between the human and the computer. Now I have this, and I can give feedback here and say, yeah, this is good. It's move it a little to the right, save it. We have another test image. Then it will process more images and give me what it found, and then I can annotate those with OK or change. So we can get a good data set quickly. But yeah, I think this is a long stream already. 1 hour. Yeah, let's cut it here. Nice little exercise.